Hey guys, I'm Pat Kelly. Okay, in this problem, they tell us to use partial fractions to find the indefinite integral. And partial fraction work with integrations are really kind of a cool thing because it can take a rational expression like what we have on the inside here and make it something simpler for us to handle, at least in terms of the integration. Okay, and the directions, of course, said something about the partial fraction work that we're going to do. But you eventually get to the point where you decide that partial fractions is going to be a good tactic for this particular problem. And a little bit of insight there for me is that when I see a rational expression, so a polynomial up top and a polynomial on the bottom, and furthermore, when the denominator polynomial is just begging to be factored, I might think of the partial fraction approach. Okay, so let's try that. In fact, it's actually always your first step with a partial fraction problem is to factor that denominator. In the numerator, some people might try to factor that, and well, some people might succeed, but whether you factor successfully or not in the numerator is not going to matter. So leave it alone. It's actually better off. It's the denominator that's the key. So downstairs, I'm going to suggest again that this is begging to be factored because you can easily pull an x out. And actually what's left over then is x squared minus 4, difference of squares. So I'll factor that as well. X plus 2, x minus 2. Right? And then dx, I guess. But those two integrals are equal. Now I'll go off to the side here, though, and do my partial fraction work. Partial fraction. Let me say partial fraction decomposition is what some people will call it. But this is side work, it's scratch work if you want to see it that way. And I'm just going to pluck the rational expression out. I'm not doing any calculus over here. I'm just going to do some algebra on that x squared. Actually, I'll grab this one. Plus 12x plus 12. Grabbing this one because I want that factored version of the denominator. So x plus 2 times x minus 2. And the whole idea of partial fraction decomposition is you're going to take this rational expression and write it as something that's equal, but again, simpler to deal with in terms of our integration. Okay? And the way we set up our work for partial fraction decomposition is with the factored version of your denominator, you're just writing smaller fractions that have those denominators. And mine only has these 3 factors, and each of them is actually only to the 1 power. And furthermore, each of mine is actually only linear. Okay, so I only have x to the 1 power in each of these, and I don't have any powers for each of for any of the factors. I'm mentioning all that because in later problems you have to address those issues. Issues is too strong of a word. It's not like they'll cause problems, but make sure you address them. If this had a 2 power, or this had a 3 power, or if this had an x squared inside. Okay. When they're linear, all you need to do is write unknowns. Your A, like capital A, and then I would put plus. And I string along for each of these factors. Each one gets its own fraction. And if your factors had higher powers than just 1, you'd have that factor represented more than once. I hope that sounds somewhat familiar to you. And again, I'm really kind of sketching that out, not for this problem, but for other problems that you do. So I only need x plus 2 once. It's linear, so I only have a b up top, plus my last factor of x minus 2, I only have it once. And I'll put a c up top because it's linear as well. Okay, and the work you do with partial fraction decomposition is really focused on finding the a and the b and the c, which I already alluded to is algebra. So take this entire equation and imagine multiplying both sides of the equation by this whole denominator. On the left-hand side, if I multiplied by that denominator, the denominator's gone. So all I'd be left with is the x squared plus 12x plus 12. And on the right-hand side, again, if I multiply the entire right-hand side by this denominator, in the first fraction, the x's would cancel, and that a would only need to multiply by these two parentheses here, x plus 2 and x minus 2. So I'm going to take a and multiply it by, well, let's call it x squared minus 4, right? Because that's what x plus 2 times x minus 2 would be. Plus the b, and in this case, the x plus 2 would cross out with this x plus 2. And I'm only left with multiplying the b by that x and the x minus 2. So let's say x squared minus 2x. And finally, the plus c will be multiplied by the x minus 2's will cross out. I'll just have x times x plus 2. So c is going to multiply by x squared plus 2x. Okay, all right. Now, at this point, it's really kind of like a balancing game is the way that I always see these partial fraction decomposition problems. And the balancing is that on the left-hand side, you can see that you have 1x squared. And you've got to have 1x squared on the right-hand side too, then to balance. Similarly, I've got 12 x's over here. I have to have 12 x's on the other side. I have 12 as a constant on the left-hand side. I've got to have 12 on the right-hand side. Okay? So I'm going to go one more step and do just a little bit of distributing through the parentheses, but then also regrouping, because what I need to focus on right now is how many different x squareds do I have? So here you can see you're going to have ax squared plus bx squared plus cx squared. And I'd like to write that as a plus b plus c x squared. Right? I actually just distributed through each of those parentheses, but then grouped together the like terms that had x squared as the variable component. And I'll do very similar work with my x, looking at minus 2bx and plus 2cx. Let's write that in parentheses as minus 2b plus 2c times x. A little bit more to go, but if you see my thinking here is I'm going to do my balancing act in a minute. And I will now know, or maybe in a minute I'll know, a plus b plus c is how many x squareds I have over here, and I need that to balance with the 1x squared that's over here. Minus 2b plus 2c is how many x's I have over here. I need that to balance with the 12. All right, let's finish this with the constants. I'll say plus, and I like to group my a's and b's and c's in parentheses, minus 4a. And this actually works out nicely for me as I don't have any other constants with the b and the c. So this is actually just minus 4a. All right, that was all algebra, and actually even a little bit more algebra. Now trying to find out the exact values for a and b and c using your balancing act. So my a plus b plus c, that's how many x squareds I have over there. Let's see if I can do it here. A plus b plus c must equal 1, right, to balance the x squareds. Okay, my x term has a minus 2b plus 2c. And if these two sides of the equation are going to balance, that's going to have to equal 12. Right? Okay, and then finally, my minus 4a is going to have to balance with the only constant on the left-hand side, which is 12. And when I had that happening a step ago, I was maybe a little bit excited about that because, I mean, the fact that there were no other constants besides the minus 4a. I was excited because you immediately get a value for one of your unknowns, your a, b, or c here. We immediately know that a equals minus 3, right? So that's good. I like that. So I'm actually going to use that then back over here. This is, I should point this out, you probably see it. It's a system of linear equations, right? So you can do whatever method you like here, whether it's substitution, elimination, Some people know to put it in a matrix and maybe reduce. Use whatever method you know to solve a system of linear equations. This one works out pretty well to do what's technically called back substitution, but I take a equaling -3 and put it in here. And that tells me that b plus c equals -3. I'd have to add over to the other side. I'd get 4. Okay. Then I'm going to take this equation and this equation, and actually I'd like to divide this equation by 2 to make it a little bit simpler and friendlier. If I divide by 2, I get minus b plus c equals 6. You notice I kind of lined it up with the equation that I just wrote down, because this will be a very convenient adding of 2 equations. So b plus or minus b, that'll be gone. This will be a 2c equals 10, and so c equals 5. Feeling pretty good. I got 2 of my values. And now in order to figure out b, I'll take my c. I can grab whatever equation's easiest. I think this one's pretty easy right here. b plus 5 equals 4. So b equals -1. All right. So I pause there. I take a breath because maybe I want to pat myself on the back a little bit. But all that algebra is great. It's good work. You've got values for a, b, and c. And why did we do that? Because now wherever in the world of mathematics that we see this rational expression, I'm allowed to replace it with those 3 smaller fractions with the specific values of a and b and c. So it's going to help us immensely with this integral. So let's get back to that integral now. All right, using all of this work, I can now rewrite this integral as the integral of, and I've got my I on the right-hand side of the equation over here, a over x, but I know my a is -3, so -3 over x, plus, I'm looking at this right-hand side, b over x plus 2, but my b is a -1, so -1 over x plus 2, plus, still looking at this, c over x minus 2, but my c is 5, so 5 over x minus 2. Let's put a nice set of parentheses there to keep it all together, because it all actually is still the integrand. Okay. But the huge benefit now is I'm doing the integral of a sum, which you know is the sum of the integrals. So I'm actually just integrating each of these little fractions separately. And they integrate very easily. First, the numerators are all just constant factors. They're not going to matter at all. So like this -3 I can pull out in front. And, well, let me write it out this way so we can actually see it very clearly at first. The -3 is out in front. I get 1 over x dx. The -1, again, a constant factor I can pull out in front. And so I get 1 over x plus 2 dx. And then finally the plus 5 integral 1 over x minus 2 dx. Right? The integral of a sum is the sum of the integrals. I try to build up to this so that you could see it very clearly. Each one of those integrals is so easy to integrate. It's an ln, right? It's just one. This one is glaringly obvious. 1 over x, that's what we learned to be the ln. These two, if you don't quite see them yet, it would be a u substitution. But the u equals would just be whatever the denominator is, and then du equals dx. So they immediately integrate into, first one, -3 natural log of x. Subtract from right there the natural log of x plus 2. I'm not saying it, but I'm writing it. Do you remember that there are these absolute values around your arguments of the ln's? Plus 5 ln absolute value of x minus 2. Okay. Let me squeeze it here, if you don't mind, the plus c, because that's all I need for my final answer. I'm done, right? The original integral that they gave me equals these 3 ln's and plus c. That's it, okay? Partial fractions, the decomposition that we do is just, it's a lot of algebra, it's a lot of good algebra. But keep your eye on the goal. The goal is to take a very complicated looking rational expression and make it something simpler that's really easy to integrate. All right? Okay, go practice some more on your own.